So previously we had seen how we could take a DFA and build a corresponding regular expression. We did it inductively, and we'd seen that even though you can do this, it's fairly expensive. In fact, if you give you an expression, the time it might take an exponential amount of time to carry out. Namely, because of the lengths of the regular expressions, they may potentially grow by a factor of 4 each time you do a round, right? So with that being said, I'm going to carefully go through an example here. So I'm not going to be going through any of the optimizations you can do with this approach unless somebody was interested in that. In my notes, I defer to a source for which you can learn more about that. But let's do an example of applying this construction that we could take any DFA and produce a regular expression. I stress this over the intermission that you could take even, like, the proof doesn't matter. It could also be an NFA if you wanted it to be. It doesn't matter. That's the way the proof doesn't depend on the fact it's deterministic. Okay. So previously we'd seen this DFA, so let's use the same one. We're going to have 2 states. Where 2 is going to be the final state. We're going to transition on a 1 to state 1 to state 2. On symbol 0, it stays in state 1, but it could stay in state 2 if it reads a 0 or a 1. So our DFA is going to be over 0 or 1 for the input symbols. It's going to have 2 states. So let's consider an example of building. So we're going to build a regular expression from DFA D, where this is D. So please note that this DFA, if you haven't thought about what language this accepts on, it accepts on those for which there exists at least one, right? To get from state 1 to state 2 requires me to read at least 1, right? So that's what the language of this DFA is. So keep that in the back of your mind. So just gonna make a couple of quick remarks. So just to make it easier is that I labeled the states where the start state is 1, the final state is 2, so all the other states other than the start state are 1. So start state's 1, everything else, maybe whatever else. So I have 2 states. State 1 is the start state, state 2 is going to be our final state, for example. So please keep that in mind. N is equal to 2. So what's exactly our goal then? So what's the goal for our computations? So what exactly do we need to compute? So we need to compute R, 1, 2, where we consider all the vertices, right? Or states. So we have to go 0, 1, then 2 for the values of k, but we specifically want the one that takes us from 1 to 2. So this is in fact this is the specific expression that's going to represent the language of our DFA. Remember, if there were more final states, you would perform union operations between each one of their corresponding expressions. So what we're going to do is we're going to consider rounds, as I talked about in our proof. So consider rounds k is equal to 0, 1, 2, all the way up to n. So in our case, we stop at 2, right? These are our rounds. So once you get the basic parts of it, you're going to work your way up from 0 upwards. So what does that mean? We're going to start off when k is equal to 0. So let's start off with k is equal to 0. So let's consider for every 0 is less than or equal to I, where I and j, actually it's going to be 0 is less than or equal to I or j, up to n for rij 0. So we're going to try to compute rij for round 0 for all the 0 paths, right? That's what these are. These are going to be 0 paths as we defined them previously. So we're going to do this for each one of these values of I and j. And remember, n is 2, so it's not going to be too terribly big our example here. But I warn you, if we had many states, this might be fairly expensive to pull off. So there's going to be 4 names for 4 expressions. Each one is going to represent a different value of I and j for round 0 when we're considering 0 paths. So we just pull out our construction we had from our previous part here, from the proof that we had, and we're going to compute each one for each I and j. So we actually had cases for each one of these. So notice that I and j here are exactly equal to each other. So you know that you're going to include the epsilon term for our regular expression right away. You do the same thing also with this one here where you have 2, 2. You know right away those are going to include an epsilon in there. Well, notice that in our DFA, if I want to go from 1 to 1, how can I do that? Remember, it's also when k is equal to 0. So all of the intermediate vertices have to have label 0 or MO0, right? It can't be, but all of these are 1 or higher. So it means that there is no intermediate vertices. That means that if I want to go from 1 to 1, notice that there's just a self loop here that takes me there and it's on a 0. So this is what the regular expression would be for R11 on round 0. Remember, this represents all 0 paths from 1 to 1. So let's consider all 0 paths from 1 to 2. So to go from 1 to 2, well, we actually discussed this when we first seen this example. I can go from 1 to 2. The only way is I read 1, right? So all strings that would get me from 1 to 2, their label would be corresponding to this expression. Then 2, 1, 2, 1. To go from 2 to 1, notice there is no way to go from 2 to 1. There is no symbol that takes me from 2 to 1. Like, even if I ignore the fact that there's no intermediate vertices, right? There's no way to go from state 2 to state 1. And lastly, we have this one for R22. Well, if I'm in 2 and I want to stay in 2, I could take a 0 or 1. It will take me here, but I'm only allowed to do this once. And there you go. So now this is for k is equal to 0. Let's consider now k is equal to 1. Now to do k is equal to 1, we have to apply the inductive part of the definition of our construction, right? Which relies on k is equal to 0. Because to go to the next step, you have to consider when k was 1 smaller. So when we consider k is equal to 1, we use the inductive part of the definition of the construction, right? Now we got to be careful when we do this. I like to think about it when we do this kind of stuff as we think about it like filling in blanks. So please remember that we had it look like this, right? So to go from I to j, right? You did it on round k minus 1. Then you could go I to k on round k minus 1. Then you have it where you could do this rk to k on k minus 1. You do that 0 more times. And then lastly, you go from k to j on round k minus 1, right? This is the inductive definition. So this is what we're going to be using. Now, when you look at this, what I want you to instead think about this like is filling in blanks. So we have 4 blanks. So wherever you see the appropriate definition we have over there, you're going to fill it in the blank. So let's do an example what I'm referring to. So just to make this a little easier for us, I'm going to try to write it a little bit more over here. So to get R111, for example, let's use this definition. So it says to go R11, remember round is 1, so k is equal to 1. So whenever you see k, that's 1. So if we apply the definition, it says R110, right? That's I and j are 1. but it's k minus 1, so k minus 1 is 0, right? Union R11, Then what we do is we apply this one here. Remember, that's 1, 1, 0. Star. And then we have R11, 0. This one's not terribly surprising, right? But do you notice how I'm just filling in the blanks, right? Wherever I have K, wherever I have K or J or I, I'm just filling in the blanks for that given value. So similar to what I've got there, I have 1, 1, 1, 2, 2, 1, 2, 2. I'm going to have one row for each one of those. But I'm going to just do for this example, I'm going to just show you what these would look like. So now I'm just going to fill in what each one of these are for their definition. Then I'm going to simplify. So R11, that is epsilon plus the expression 0. That's what this is. Okay, now we got to do 3 concatenations here. So now we got R110. Well, it's the same thing, right? All of these are the exact same. They're all the same, right? But if you actually look at this carefully, what I've written here is actually a lot of redundancies, right? So if you actually look carefully at what I've written here, what does this look like? Okay, you got epsilon or 0. Or you got epsilon or 0. Epsilon or 0, 0 more times. Epsilon or 0. Notice that this is an option, that's an option. So you could, technically speaking, you could just have epsilon over all of this, right? You get epsilon, you could take a 0, right? You could take 2 zeros. You could take 3 zeros, for example. You can have 0, 0, 0. You get 4 zeros, 0, 0, 2, do this twice, and then there's a 0 there, right? Do you notice that this actually just captures 0 star? So this right here is actually simplifies to, so this simplifies to 0 star. So I'm putting that step in there just to make it a little easier for us to follow through. Otherwise, like I said, these expressions get very, very long. Like I said, notice that R110 looks like this. That's like 4 times as long almost, right? It's got, actually, it is pretty much 4 times long, right? The length or description of it is 4 times as long. At least, right? It's got 1, 2, 3, there's 4 of them. So let's do the next one. So let's consider now R121. Well, what is this? This is R for round 0, 1, 2, right? Or I got R11, 0. Remember, it's round 1 still, right? So K is 1. R11, R110 star. And then lastly, we go from K to J. R12 on 0. So let's see what that is. So just to make this a little easier for myself, I'm just going to kind of move that up like that. So let's fill in the blanks. So just remember to fill in the blanks. There's 4 blanks. Then simplify. So let's go. Let's go. So R120, that's just 1, right? Or we get R110, so that's the same as we had before, epsilon or 0. Then we have epsilon or 0 star. And then we have R120. 120, that's just a 1, right? But now, let's take a look at what we got here going. Let's simplify this just to make it easier for us later. You can have a 1. You can have no zeros, right? You can take a 0 or not. You could take a 0 or not. and do it as many times as you like, then you have a 1. Do you notice that you always have to take a 1, right? But you can have 0 or more zeros. So this actually simplifies as well. If you understand it, it actually is just simply 0 star 1. Now let's do the next one. R21, 0. Okay. So this is R21, 0. Or R21, 0. Then we have R11, 0 star. And then we have R11, 0. Because remember, it's 2, 1. I is 2. J is 1. K is 1. Now we're going to fill in the blanks. So we have R210, that is just the empty, that's the expression for the empty language. Or we have the empty language concatenated with epsilon or 0 star. And then you have epsilon or 0, right? But now, if we simplify this, take note of what's going on here. The empty language, or the empty language concatenated with something, Now, there's a really neat property that these empty languages have when you consider them in concatenation. Because remember, that is the empty set. Remember, that's what the empty language is. If I give you a regular language, and I give you the expression for the empty language, if I concatenate these two, this is actually equal to our empty language, and this is actually equal to the empty language. You might say, Dan, why is that the case? It's because notice that by definition, concatenation over a language is where you take each string in one of them and you concatenate it with each one in the other one. But there's none in here. There's none in there. It's an empty set. So that means that you're taking nothing, concatenating against something. So that means that you have nothing, right? There is nothing. It contains no strings. This simplifies to the empty language. So the expression for the empty language. And last, we have the last one here. So we got R221. This is equal to R0. So for round 0, it's 2, 2. Or we have R21, 0, R11 for round 0 star. And we have R12 for round 0. So what's this? Well, let's see. Let's fill in the blanks. So R022, that's epsilon or 0 or 1. Or we have R21. The minute you see the empty language, you start doing concatenations. You know it's going away, right? So you have empty language concatenated with what? Epsilon or 0 star concatenated with 1. But remember, as I said, when you concatenate like this, you end up with this. But also another property I want you to be aware of is that if I have the empty language and I union it with some other regular language, like, so this is the expression for that regular language, as per the regular operator that I've denoted like this. This is the same as writing just that. Think of it, just remember, go back to the definition if you're not convinced by this. This is the empty set or an empty language. This is some language that may have some strings in it. So the union of an empty set with something with stuff in it is the something with stuff in it, because the empty set doesn't contribute anything. So let's simplify this now. So that means that all of this, because of what we described earlier about concatenation, this is just going to be simplifying just to this first part. There. Now we did round 1. So let's consider when k is equal to 2. We apply the inductive part of our definition. So remember, fill in the blanks. Fill in the blanks. So just remember, that is our best friend for doing this. So now, since n is equal to 2, that means that when we consider k is equal to 2, this is the final round. If we, for example, had 5 states, then you have to go up to k is equal to 5. So I'm going to make a table here. We're going to do this carefully. So rather than going through row by row, I'm going to fill in the blanks for each one of these for their expressions themselves. Then we'll fill it in together because we have to do it a bit more carefully because I've done some simplifications for us here. So we got R112, right? We got R122. We have R212. And we have R222. Well, what's this one? Well, let's look at that definition for each one of these. So this should be equal to R112 or 1? It's 1, right? Or R121, because remember k is equal to 2. Then we have R221 star. Remember, k is equal to 2, so we just put in 2 wherever we see k. And then we have R21, 1, because remember, j is equal to 1. So that's that one. This one is R121. In fact, all of these, you'll notice that they're all just that, right? They're just always with 1 k less. Now it's just a matter of the other part, So we got R1, 2, 1, R2, 2, 1 star. And then we have R2, 2, because remember j is 2 in this case. 1. Then we have 2, 2 here. 2, 2, 1. Then we have R2, 2, 1 star. Then we have R2, 1, 1, because j is 1 in this case. Then next we have R2, 2, 1, R2, 2, 1 star, R2, 2, 1. So here's our table here. I'm going to extend this out now. So let's fill in the blanks now. Now we have all of these. We have them over there. So we have to be careful here because I've sort of lost our expressions, what each one corresponds to. This is the first row. That's the second row. That's the third row. That's the fourth row for each one of these where you replace those with a 1. So let's do this. So R111, that is just simply 0 star, right? So this is just simply 0 star. So this is a direct computation of what it is. Or we have 1, 2, 1. So that is 0 star 1. 0 star 1. Then R2, 2, 1 with the star. 2, 2, 1. It's epsilon or 0 or 1. And we apply a star onto that. And then lastly, we have R210, which is the expression for the empty language, right? And the minute you see that, you're like, oh yeah, all of this is going bye-bye. This is all going bye-bye. So this simplifies down. This simplifies down to just simply being 0 star, because that's all I'm left with. So this is our direct computation, and this is our simplification. So let's proceed now. We got 0 star 1. So 1, 2, 1. Yeah, 0 star 1. Or we have, what do we got here? We got 1, 2, 1. So we got the same thing again. 0 star 1. And then lastly, we have 2, 2 again. Our friend 2, 2 appears twice. Epsilon or 1 or 0 star. And then we have epsilon or 0 or 1. Sort of running out of space here. Gotta be careful. Okay. So now, let's see. We had 0 star 1. Then we have 0 star 1. Where I have epsilon, 0, or 1. So I get a choice of 0 or 1. But I could do it how many times? Well, let's see. Notice that immediately after this, I have epsilon. So I get the choice of not picking any one of these. So actually, I can do it 0 or more times this part here. So do you notice that that's actually, this is no different than me writing this. It's 0 star, 0 star, 1, where I concatenate this with 0 or 1 star. Like that. Why? Because remember, I have an option right here. If that was not there, I would be required to concatenate an additional 1 or 0. So let's proceed now. Now we got the next 2. We have the empty language right away. 2, 1. 2, 2. So we got our friend 2, 2 again. But you'll notice that there's a 2, 1 right here again. So we're going to have epsilon or 0 or 1 concatenated with epsilon or 0 or 1 star. And then the empty language. That means that this is all going to get annihilated because of this concatenation here at the end. And I already had the empty language over there. So this ends up being resulting as the empty language, or the expression for it to be a bit more precise. Then lastly, we got this one here. Let's see what we get. Wow, 2, 2 is everywhere. So you can see right away this is going to be epsilon or 0 or 1. Or I get the choice of epsilon or 0 or 1 concatenated. So this is going to concatenate with epsilon or 0 or 1 star. And that is going to get concatenated with epsilon or 0 or 1. But what is this? Well, think about it. I could pick nothing. I can get 0 or 1. I can then get, so I get a choice of none of it at all, right? I could get a 0 or I could get a 1. I could get 1, 1. I could get 2 1s. I could get 3 1s. I could also get 1 0, 2 zeros, 3 zeros, and so on. Notice that this is no different than me writing this. 0 or 1 star. So now you might ask, Dan, you computed all of them for k is equal to 2. Do you actually need to do that? And the answer is actually no, I don't have to. I'm just doing it for the sake of you understanding how we apply this construction. But there's only specific rows in this computation that actually matter because we're on the last round. If that were not true, it may be the case that you actually need to compute all of these. So notice which one is the one that we really care about. Well, we go from the start state to the final state, and there's only one final state, right? State 2. State 1 is the start state. So what row do we actually care about? It's this one right here, right? If we had multiple final states, like if, say, state 1 was a final state as well, then you would also have to include the appropriate rows for those as well. And you just apply union operations. Thus, R12n is equal to R12, 2, which this is 0 star 1 or 0. So we concatenate this with 0 or 1 star. Which, if you remember, when we first introduced this example last time, this gave us actually the exact same one we had for our intuition when we were computing the 2 paths from 1 to 2. That's the exact same expression we came up with. And that is exactly the one that appears on that row over there.